All right, this is question number 1 from the 2010 AP Calculus AB exam. It's what I call a rate FRQ. And what we're given here is a situation where we've got this person, Janet, who's got no snow on her driveway. When the snow begins to fall at midnight, and from midnight to 9 a.m., it accumulates at this rate f of t. That is 7t e to the cosine t in cubic feet per hour. And then at 6 a.m., she starts shoveling this snow. She starts removing this snow at a rate g of t, which is piecewise function. So her rate is 0 from 0 to 6, and then 125 cubic feet per hour from 6 to 7. Then she slows down a bit to 108 from 7 to 9. We just want to know how many cubic feet of snow have accumulated on the driveway by 6 a.m. So from t equals 0 to t equals 6. So in order to get the amount that has accumulated on the driveway, we just have to integrate the rate. So we're just going to integrate her rate, or not the rate, but the rate that it falls from 0 to 6, right? We're going to integrate 7t e to the cosine t dt, or you can just write the integral from 0 to 6 of f of t dt. And this being a calculator question, so we'll just go to our graphing calculator, and we'll do math, option number 9, and we'll integrate from 0 to 6. And our function was 7t, so we'll do 7x, and then e to the cosine t, so we'll do e to the cosine x. And of course, we'll put our dx out here since that's our variable, and we end up getting 142.275 cubic feet. And that's worth 2 points. 1 point for the integral setup and 1 point for the answer. In part B, it asks what the rate of change of the volume of snow on the driveway at 8 a.m. is. So if we had a function that represented the amount of snow on the driveway, let's call it, I don't know, we've got f and g, so let's call it h. If h of t is the amount of snow on the driveway, we'll call h of t the amount of snow on the driveway, then h of t should equal the integral of f of t from, well, we'll call it f of x, from 0 to t, minus the integral of g from 0 to t. And so basically, if we want to find the rate of change of that volume of snow, right, and we're subtracting the g of t because that's how she's removing it. So the rate of change, h prime of t, should just equal f of t minus g of t. And if we want the amount, or the rate of change of the volume of the snow at 8 a.m., we want h prime of 8, which will be f of 8 minus g of 8. And f of 8 minus g of 8. In fact, you don't really need to do all of this stuff here. You can just say the rate of change is f of 8 minus g of 8. But I think it's nice sometimes to have the function itself in case we need it at a later point, which we often do in these rate questions. So we'll just do f of 8 minus g of 8. We can see that g of 8 is 108. So we'll just find f of 8 on our calculator. So that'll be 7 times 8, or 56, e to the cosine of 8. That'll be f of 8. And then we're going to subtract g of 8, which was 108. And we end up with negative 59.583 when we round there. And if we want units here, it's going to be feet cubed per hour. And they just gave you 1 point for that part. In part C, they said let h of t represent the total amount of snow. In this case, it's the total amount of snow that Janet has removed from the driveway at time t equals, or t hours after midnight. And we want to express h as a piecewise function defined with domain 0 to 9. So I guess we maybe shouldn't have called this one h. We'll just call it h sub 1. How about that? That way we don't have the same function again. Not that it really matters. So we know that we need to find the function h of t that's the total amount of snow she's removed. Well, if she's removing it at 0, from 0 to 6, well, then h of t, since h of t is going to equal 0, right, for 0 to 6, right? Because if she's not removing anything, then there's no amount that she's removed. Like if her rate is 0, she's not removing anything. So from 0 to 6, she's removed nothing. Which means that we also know that h of 6 is equal to 0, right? We'll note that off here. H of 6 is 0. By the time she's gotten to 6 hours, she's removed nothing. Well, the value from 6 to 7, right? From 6 to 7, so we're going to put this in here for 6 to 7, she's removing it at 125 cubic feet per hour. So really what we want to do is we just want to integrate from 6 to t, the function g, which is 125 dt, or we'll say 125. We'll use the different variables. We'll say dx, and we want to do this and then add our initial amount at 6, right? That should tell us what the amount is at any time between 6 and 7. Well, the integral of 125 dx is just going to be 125 x, and we're going to evaluate that from 6 to t, so that'll be 125 times t minus 6, right? Or 125t minus 6 times 125, which is 750. So we can just say 125 times t minus 6. And so that would be what our function here is going to be from 6 to 7. Then we need to figure out what that actually equals at 7. So we can see that if we plug in 7 to this, we get h of 7 is equal to 125, right? That's our initial amount there at 7. And so from 7 to 9, we want to do 125 plus the integral from 7 to t of 108 dx. And so now that's going to be 125. We'll get 125 in here to start with, plus, well, the integral of 108 is 108x, so it's 108x from 7 to t, or 108 times t minus 7 for 7 to t to 9. And of course, you can simplify those if you want to, but not necessary to. And you get 3 points for that, 1 for each of the 3 pieces of it. And in part D, it asks how many cubic feet of snow are on the driveway at 9 a.m. And so, well, we just know that we started at 0 and we accumulated whatever the integral from 0 to 9 of f of t was. And then we are going to subtract the value of h of 9, right? H of 9 was what we just came up with, right? We just came up with a function to represent h at any given value. That's how much has been removed. So if we look at our function h of 9 here, if we plug in 9 to this, it's going to be 125 plus 108 times 2. Right? H of 9 is 125 plus 108 times 2, right? Or 125 plus 216. So what does that come out to be? That comes out to be 341. So we're looking at the integral from 0 to 9 of f of t minus 341. So we'll do math. Option number 9, we're going to do an integral from 0 to 9 of our function 7x e to the cosine x dx. And then we were going to subtract 341 from that, which gives us 26.335 when we round. So 26.335 cubic feet. And that was worth 3 points. 1 for just having the integral, 1 for having the correct value for h of 9, and 1 for the final answer. And that is it for this rate FRQ, which was the first question from the 2010 AP Calculus AB exam. All right, this is question number 3 from the 2010 AP Calculus AB exam. It's another rate FRQ. We're given a graph here of R of t, right, which is, it's a rate at which people arrive at a ride at an amusement park. And the question tells us that we have 700 people in line for this ride when it begins operation in the morning. And when it opens, it accepts passengers for 8 hours until it closes. And while there is a line, people get on the ride at 800 people per hour. And this graph is telling us the rate at which people arrive at the ride. So this is the rate at which they get into the line, basically, and then 800 people per hour get onto the ride. We want to know how many people arrive at the ride between t equals 0 and t equals 3. So in order to figure out how many people get on the ride between t equals 0, not how many people get on, but arrive at the ride from t equals 0 to t equals 3, we just need to integrate r of t from 0 to 3. And to integrate r of t from 0 to 3, we just have to find the area underneath this graph, right? And so the area underneath this graph can be broken up into 2 trapezoids, one from 0 to 2 and one from 2 to 3. So the trapezoid, we kind of look at them on their sides. The trapezoid from 0 to 2 has a base of 1,000 and another base of 1,200 up here. So it'll be 1,000 plus 1,200 divided by 2 times the height there of the trapezoid, which is 2. And then we'll add to it the other trapezoid, which has a base of 1,200 and another base of 800. So 1,200 plus 800 divided by 2 times the width there, which is just 1. And so if we evaluate this, right, we are basically getting 1,000 plus 1,200, because the 2's will cancel here. That's 2,200. And then plus another 1,000 from this piece, right? 2,000 divided by 2 is 1,000. So we end up with 3,200 people arrive at the ride during the 8 hours. And you get 1 point for just recognizing that it's an integral from 0 to 3 of r of t, and 1 point for the answer there. For part B, we want to know, is the number of people waiting in line to get on the ride increasing or decreasing between t equals 2 and t equals 3? So the number of people waiting in line to get on the ride. Well, we know that the rate that they get on the ride is 800. And if we look, r of t is representative of the rate at which the people are arriving at the line, right? And so all we really need to do here is see if the rate that they are arriving is greater than 800. And so we can see that from 2 to 3, right? Here's 2 and here's 3. The rate at which people arrive goes from 1,200 to 800. But for that entire interval between 1,200 and 800, that rate is always, or that interval between 2 and 3, that value is going to be more than 800, right? Which is going to tell us that the number of people in line is increasing. So we'll say something like, on 2 is less than t is less than 3, r of t is greater than 800. So the number of people waiting in line is increasing. Because they're arriving more quickly than they're getting on to the ride. And they gave you 1 point for that. In part C, it says, at what time t is the line for the ride the longest? And we want to know how many people are in line at that time. And also, we need to justify our answers here. And so, in order to figure out at what time t is the line for the ride the longest, we need to kind of take into account that the ride has more people getting in line for it than they can put on from 0 to 3. But after that, the number of people in the line is decreasing because the rate is less than 800 that they're arriving at the ride. So more people are getting on the ride than are showing up to do the ride. So we can say that, we could say R of t is equal to 800 at only t equals 3. And since the rate on 0 to 3 is greater than 800, and we'll also say and less than 800 on 3 to 8, then the max is at t equals 3. And we want to know how many people are in line at that time. Well, we had 700 people to begin with. We need to add to that the amount that got in the line from 0 to 3, which we already found out in part A was 3,200. And then we subtract from that the rate at which the people move on to the ride, which is 800 for those 3 hours. So minus 800 times 3, which is 2,400. So we'll do 700 plus 3,200, which is 3,900. Subtract 2,400 to it, and we get 1,500 people. And we get 3 points here for this. 1 is for identifying t equals 3. 1 is for the number of people in the line, and 1 is for the justification, which is what we wrote out over here, that we must have been at the max because the rate was greater than 800 from 0 to 3 and less than 800 on 3 to 8. And in part D here, we're asked to write, but not necessarily solve, an equation involving an integral, an integral expression of r, right, the function r, whose solution gives the earliest time t at which there is no longer a line for the ride. Well, we want the number of people in line to be 0, right? And the number of people in line is the initial amount in line, 700, plus the integral from 0 to t of r, we'll call it r of x dx, minus the number of people that get on the ride, which is 800 times whatever number of hours we've gone past. And so this is an expression to tell us how many people are in the line at any given time. Well, we want to know when there is no longer a line, so we want to know when that equals 0. And they actually gave you 3 points for this, 1 for just having 800t in it, 1 for having the integral in it, and 1 for the equation as a whole. And that is the end of this question, question number 3, a rate FRQ from the 2010 AP Calculus AB exam. All right, this is question number 3 from the 2010 Form B AP Calculus AB exam. This is back from when the first 3 questions were calculator questions, so this is a calculator problem here. So part A, actually let's talk a little bit about it first. First we got a figure with an above ground swimming pool. It's a cylinder. And we got some dimensions for it, radius of 12, height of 4. And water is pumped into the pool at this rate P of t, which is given in the chart. And then on that same time interval, water is leaking from the pool at R of t. And of course, they've given us R of t here, 25e to the negative 0.05 t. So part A asks us to use a midpoint Riemann sum with 3 equal length subintervals to approximate the total amount of water pumped into the pool. And we don't care about how much is draining out, but just what's pumped in on the interval from 0 to 12. So if we're going to use 3 subintervals of equal length, that'll be 0 to 4, 4 to 8, and 8 to 12. And a midpoint Riemann sum will mean we're going to take the midpoint values for each of those. So each interval has a width of 4. So we're going to do 4 times 46 plus 4 times 57 plus 4 times 62. And we'll just add those all together. And multiply and add them all together. And we end up with 660 cubic feet of water is pumped in. And you can use your calculator to do the arithmetic there if you want. And so this is our approximation here. Might be good to say this is approximately equal to the integral from 0 to 12 of p of t dt. Right? And so you got 2 points there for that. 1 point for just the setup and 1 point for the actual answer. In part B, it wants us to calculate the total amount of water that leaks out of the pool from 0 to 12. Well, in order to get the amount of water leaking out, we need to integrate the rate at which it leaks out. So we're just going to integrate r of t dt from 0 to 12. And so we'll just use our calculator to do this integral. So we're going to hit math, and we're going to go down to option number 9. Of course, you can just hit the 9, and it'll populate it. And you can do 0 to 12 for your lower and upper limits. And we want capital R of t in there, which was 25e to the negative 0.05 t. We'll just use x, because that's what we use on our calculator. And we'll go out here and do dx. And it gives us 225.594. So we'll say this is approximately equal to 225.594 cubic feet of water. And you get 2 points there, 1 just for the integral and 1 for the answer again. In part C, it asks us to use the results from part A and B to approximate the volume of the water in the pool at t equals 12. Right? And so we know that it started at 1,000 cubic feet, right? And so all we have to do really here is just do 1,000 plus our value that we got in part A, which was 660, and then minus our value that we got in part B, which is 225.594. You can use your calculator to do all that arithmetic if you want to. It comes out to be 1,434.406 feet cubed. And of course, it says the nearest cubic feet, so we'll say 1,434 feet cubed. Right? Make sure you round when it asks you to round. And they just gave you 1 point for that. Basically, they're just making sure, did you read the question? Right? What did you know that there were 1,000 cubic feet of water at t equals 0? And in part D, we're looking for the rate at which the volume of the water in the pool is increasing at t equals 8. And then we also want to know how fast is the water level rising. So to find the volume of the water in the pool, right? The volume of the water in the pool, V, should equal, we'll call it V, should be equal to the amount of water that was in the pool plus the integral of the rate at which it's being pumped in, right? 0 to t of capital P minus the integral of the rate at which it drains, which was capital R. And so to find the rate at which that volume is increasing at t equals 8, we want v prime. Well, v prime is just going to be the derivative of 1,000, which is 0, and the derivative of p, or the derivative of the integral of p, from 0 to t. So that's the first part of fundamental theorem of calculus. That's just p of t. And the same with the r. It's just r of t, right? The derivative of an integral from a constant to a variable of a function is just the function in terms of that variable. And so to find that rate of change of the volume, we want v prime of 8. So that should be p of 8 minus r of 8. And of course, p of 8 is 60. And r of 8 we'll get from plugging it into our function there. So we'll just use our calculator here. P of 8 we knew to be 60. And r of 8 is 25 e to the negative 0.05 times 8. Well, negative 0.05 times 8 is negative 0.4. And so we just need to calculate what that is. And it is 43.242. And our units here are feet cubed per hour. It says include units of measure in both answers, so that's going to be feet cubed per hour. And then it asks us, how fast is the water level rising at t equals 8? Well, that's the h value, right? So we're going to get a new page here. If the volume is pi r squared h, and the radius is not changing, but the height is. So the radius was 12. So we know that v is actually equal to 144 pi h, right, since the radius was 12. And so we can take the derivative of this with respect to time, getting dv dt is equal to 144 pi dh dt. And we have dv dt. We already found dv dt in the previous part of the problem, right? So dv dt, if we look back here, right, the rate of change of the volume when t was 8 was 43.242. So we've got 43.242 divided by 144 pi should be equal to dh dt. And if we go over here, we can just do that number divided by 144 pi. And it looks like we get 0.096. And this time it's height, so that's feet. And then divided by the hours, feet per hour. And this was worth 4 points here. So they gave you 1 point for getting the 43.242. They gave you 1 point for this v equals 144 pi h. Or actually for taking the derivative of it. So they gave you 1 point for this equation, dv dt is 144 pi dh dt, 1 point for the value, and 1 point for having the correct units for both of those answers. And that is the end here of question number 3. It's a rate FRQ from the 2010 Form B AP Calculus AB exam. All right, this is question number 1 from Form B of the 2011 AP Calculus AB exam. It's a rate question. And we've got a cylindrical can with a radius of 10 millimeters measuring rainfall. Initially, it's empty, and rain is going to enter between t equals 0 and t equals 60. The height of the water is measured by s of t, and the rate at which that height is rising is given by s prime of t here, 2 sine of 0.03 t plus 1.5. So first off, it wants to know what's the height of the water in the can at the end of the 60 days. Well, in order to figure out how much water accumulates in that can, we just integrate the rate. So we're just going to do an integral of s prime of t dt from t equals 0 to t equals 60. And conveniently, this is a calculator question, so we will just punch this in to our graphing calculator. We're going to hit math, option number 9, FNINT, and we're going to do an integral from 0 to 60. And the function s prime was 2 times the sine of 0.03t, so we'll use x. Close the parentheses on your sign, and then we had a plus 1.5 after that, dx. And so it gives us 171.813 as our answer, 171.813 millimeters. And so they actually gave you 3 points, surprisingly, for this. 1 for having the correct limits, 1 for having the correct integrand, s prime, and 1 for having the correct answer. So in part B, it's asking us to find the average of the rate of change in the height of the water in this can on the 60-day time period. And so if we want the average of a function that represents the rate of change, well, the average of that function should just be 1 over b minus a. In other words, 1 over 60 minus 0 times the integral from 0 to 60 of s prime of t dt. And so we'll just use our calculator to just essentially just do what we already did, but just divide it by 60. So from part A, we had an answer of, we'll just go back to our calculator here, 171.813473. We just need to divide that by 60, and we end up getting 2.864 millimeters per day. And they just gave you 1 point there for part B. In part C, it says, let's assume that no evaporation occurs. We want to know at what rate is the volume of the water in the can changing. So not just the height, but the volume. And so our volume, this is a cylindrical can, so the volume of a cylinder is pi r squared times the height, right? And so our height is given by s of t. And so we have pi times our radius of 10 squared times s of t, or in other words, the volume is 100 pi times s of t. And so we're looking at what rate is that volume changing. So we need to take the derivative of this with, with respect to t, which it's all in terms of t, so that's easy enough. dv dt is just equal to 100 pi times s prime of t. And if we're doing this at 7, right, v prime of 7 is just going to be 100 pi times s prime of 7. And our calculator will help us to find the value of s prime of 7. So we'll just do on our calculator 100 pi times s prime of 7. And s prime, we knew it was 2 times the sine of, now we've got 0.03 times 7, because it was 0.03t. And then we still have a plus 1.5, and we end up getting 602.218. It says to indicate units of measure. And so this was in millimeters initially, so these will be now for volume, millimeters cubed per, t was in days, so millimeters cubed per day. And they're going to give us 2 points here, one for the relationship that we found here between the volume and the s. So basically, I'm getting 100 pi s of t for volume, and 1 point for the answer with the correct units. And then here in part D, it says during the same 60-day time period, we've got rain on some mountain, Monsoon Mountain, is accumulating in an identical can. The height of that water in that can is modeled by m, which is given to us. And the same units. And we have d of t, some function d of t, that's equal to m prime minus s prime. And it asks us to apply the intermediate value theorem to the function d on the interval 0 to 60 to justify that there's a time when the heights of the water in the cans are changing at the same rate. Well, if the heights of the cans are changing at the same rate, that means, right, that m prime is equal to s prime, or in other words, m prime minus s prime is equal to 0. So we'll say m prime of t equals s prime of t if m prime of t minus s prime of t is equal to 0, right? So basically, if d of t is equal to 0. And we'll note that the function d must be a continuous function, right? We'll note that d, which is m prime minus s prime, is continuous. And we know that it's continuous, right? Because, m has a derivative, right? And s has a derivative, and m and s were both continuous functions, right? And the rate of change, it's never going to be an undefined rate of change, right? There's always going to be some value, and it's, we can't have any like breaks or holes in that. So we know that this function is continuous on 0 to 60. And so all we have to do is show that m prime minus s prime is greater than 0 at some point, and that it's less than 0 at some point. And so, and we can call it d also. So we're going to look at what's going on at, let's say at 0. So d of 0, which would be m prime of 0 minus s prime of 0. And, s prime of 0 and m prime of 0 can both be found pretty easily, right? We'll just use our calculator here to find m prime of 0 minus s prime of 0. So we'll go in here, and we need to find the derivative of that new function, right, of m at 0. So we'll hit math, and we're going to go down to option number 8, and we're going to take the derivative with respect to x of that function, right? And that function was, we had 1 over 400. So I'm going to hit alpha and the little x next to it to give me a nice little fraction here. 1 over 400. And then times, we had 3x to the third minus 30x squared and plus 330x. So we want the derivative of that at x equals 0. And then we want to subtract from that our function, s prime, that we started with at 0. Right? Well, if we look at that 2 sine of, in fact, let's actually just, let's just find this first. So we get this, and then if we subtract s prime of 0, it was 2 sine of 0.03t, so that part's just 0, and then it was plus a 1.5, so we just subtract 1.5 from this, and we get negative 0.675. So this is equal to negative 0.675, which is less than 0. And then we can find d of, might as well just check it at the endpoint, d of 60. And so we'll go back in, and this time, instead of retyping this whole first thing that we did, I'm going to just highlight this and hit enter. And instead of checking for the derivative at x equals 0, we're going to find the derivative of it at x equals 60. And then we want to subtract from that s prime at 60, which s prime, again, was 2 times the sine of 0.03 times t, so times 60, and then plus 1.5, which ends up giving us 69.377. And we'll note that that's positive. And so by the intermediate value theorem, so d of t equals 0, somewhere on 0 to 60, because m prime of 0 minus s prime of 0, or d of 0 was negative, and d of 60 was positive. And they gave you 2 points there for that problem. And so one of them was for looking at d of 0 and d of 60, and one was for the justification, which includes that that the intermediate value theorem, or not that the intermediate value theorem was used, but that it was continuous. Right? And then they also gave you a final point there. If you had the right units in either part B or part C, you got 1 point for doing that as well. And that's the end of question number 1, this rate FRQ from Form B of the 2011 AP Calculus AB exam. All right, this is question number 2 from the AP Calculus AB exam 2011 Form B. And it's a rate FRQ again here. So we've got a 12,000 liter tank of water that's filled to capacity. And at t equals 0, the water starts draining out of the tank. And R, the rate at which it drains, is a piecewise function that you can see there, 600t over t plus 3 from 0 to 5, and 1,000 e to the negative 0.2t for t greater than 5. Part A just says, is the function continuous here at t equals 5? Well, in order to figure out if the function's continuous, we need to use limits. So we're going to do a limit as t approaches 5 from the left of r of t dt. And we're going to do a limit as t approaches 5 from the right of r of t. Not dt. I don't know why I'm so used to doing integrals. There's no dt, just r of t. So for this one, this should be 600 times 5 over 5 plus 3, which is, of course, 5 times 600 is 3,000 divided by 8. So we get this 3,000 divided by 8. What is 3,000 divided by 8? Must be 375, I believe. Let's just check that since this is a calculator question. Oh, good. My arithmetic was good. 375. And then for the other one, this is going to equal 1,000 times e to the negative 0.2 times 5. Well, negative 0.2 times 5 is negative 1. I'm pretty positive 1,000 e to the negative 1 is not 375, but just to confirm, we'll just put it in here. I mean, it's definitely not, but we put it in, you get 367.879. So we can see that R is not continuous at t equals 5. And the reason is because the left and right limits, right-hand limits, are not equal. Right? And therefore, it is not continuous, right? It has to meet that to be continuous, right? So that means the limit does not exist there, so it's not continuous. They gave you 2 points for the conclusion there with the analysis up above to show it. In part B, it asks us to find the average rate at which the water is draining from the tank on the interval from 0 to 8. So the average rate is just the mean value theorem for integrals. It's 1 over b minus a, so 8 minus 0, times the integral from 0 to 8 of r of t dt. Well, in order to find the integral from 0 to 8 of r of t, we need to break this down into 2 separate integrals. One that's the integral from 0 to 5 of 600t over t plus 3 dt, and the other that is from 5 to 8 of 1,000 e to the negative 0.2t dt. And this is a calculator question, so we're just going to let our calculator do all the work here for us. We're going to go in here, we're going to say we want I'm going to hit alpha and then the x button to give me a nice little fraction, 1/8 of the integral. So we have two different integrals here. So I'm going to put the whole thing in parentheses. And we're going to do math and option number 9, FNINT. First off is the integral from 0 to 5 of that first function. I'm going to do alpha and the x button again to just give me this nice little fraction. We're going to put in our function 600t, or in our case 600x, over x plus 3 dx. And then still within that parenthesis, that's being multiplied by 1/8, we want to do another integral, math option 9 again. And this time it's the integral from 5 to 8 of this other function that we had, which was 1000 e to the negative 0.2t, or in our case, negative 0.2x. We'll throw our dx in, we'll close our parenthesis, and when we hit enter, we definitely put something in wrong because that's certainly not the average rate. And I can see exactly what I did here. I just forgot the plus sign between the two. So if you get an answer that just seems absolutely ridiculous, like we just did, go back up, highlight it, hit enter, and then go back through here to where you made your little mistake instead of retyping everything. And right here, I can just hit second, and then the delete key is an insert button, and it'll just let me insert a plus sign in there where I meant to have a plus sign instead of a multiplication sign. And now when we hit enter, we get something a lot more reasonable of 258.053. And it didn't really ask us about units or anything here, so that's perfectly acceptable as our answer. We had 1 point for the integrand of r of t. We had 1 point for having the right limits here on both of our integrals with this constant, and then 1 point for the final answer. Right? And I mean, you could have been pretty certain that that weird answer we got was incorrect. If you get something that big, I mean, that would have meant that this thing had drained in less than an hour, it looked like. So, and you know, that wouldn't make any sense for the average rate that it's draining to have been something that would have made it drain out in an hour when we had 8 hours. So always think about reasonable responses. All right, in part C here, we want to find r prime of 3 and then just use the units to explain what it means. So r prime of 3 means we're going to take the derivative of 600t over t plus 3 at 3. So we'll go in here, we're going to hit math, and this time it's option 8 in deriv. That's way too far. There we go. You can always just hit 8. And our function, as we just said, was 600, in our case, x. I'm gonna do this nice little fraction thing again, alpha, and then the x button. So 600x over x plus 3. And we want to find this derivative at x equals 3, which gives us 50. That was a nice number. So we're just going to write r prime of 3 is equal to 50. And what this is telling us here, right, this is the derivative of the rate. And the derivative of something tells you that whether it's increasing or decreasing, right? So this is positive. So it tells us that that rate that the water is draining is increasing. So we're going to say the rate at which the water drains from the tank at t equals 3 is increasing at 50, and then we're going to put some units on here, even though it does say using correct units. 50, and our units here were liters per hour for the rate, so it's liters per hour, or liters per hour squared. And they gave 2 points out for this, 1 for just getting the correct value and 1 for the explanation with the right units. And our last part here is write but don't solve an equation involving an integral to find the time when the amount of water in the tank is 9,000 liters. Well, we know that we started at 12,000, and we want to subtract the amount that drains. So it's going to be 12,000 minus the amount that drains from t equals 0 to some time a of our r of t function. That's going to tell us how much is in the tank at some time a. Well, we want that amount to be 9,000, so just set it equal to 9,000. Pretty straightforward one there. You get 1 point for having the integral and 1 point for the whole equation. And that is the end of this rate FRQ, question number 2 from Form B of the 2011 AP Calculus AB exam. All right, this is question number 1 from the 2013 AP Calculus AB exam. It's a rate FRQ, where they give you a rate in tons per hour at which unprocessed gravel is arriving at a processing plant. And the function is g of t, which we can see 90 plus 45 cosine of t squared over 18. And they give us a time period here. We're talking about in hours from t equals 0 to 8. The beginning of the workday is t equals 0. And it tells us that at that time we have this initial condition that we have 500 tons of unprocessed gravel. And we want to know a bunch of things about this, but it also tells us that during the hours of operation, they're processing the gravel at a constant rate of 100 tons per hour. So first off, it says what's g prime of 5, and use correct units to interpret that in the context of the problem. Well, luckily this is a calculator problem, so we can just have our calculator approximate g prime of 5. So we'll just go in and go to our graphing calculator, and we'll just do math, and option number 8 will take the derivative for us in deriv. You can also just hit the 8 instead of scrolling down. We'll do a derivative with respect to x, because that's what we have to do on our calculator. We'll put in 90 plus 45 times the cosine of t squared, so we'll do x squared over 18. I like to hit alpha and the x button to just give me this nice little fraction bar, and then we'll do x squared over 18. And it wanted us to find this value when x was equal to 5, so just put in a 5 down there. And we get negative 24.586, or 588 when we round. So we've got negative 24.588. And it says, using correct units, interpret your answer in the context of the problem. So this is a derivative of the rate. It's negative, which tells us that the rate is decreasing. So what we've got is the rate at which the unprocessed gravel arrives is, since it's negative, is decreasing at negative 24.588. And our units here, the units of G were in tons per hour. So we're going to say tons per hour, and then the derivative makes it per hour again. And we'll say at t equals 5, right? Or we could say at hour 5 of the workday, or something to that effect. And that gives us 2 points here, 1 just for getting the value, and 1 for our explanation that's got the right units. In part B, it wants to know the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. Well, the hours of operation are 0 to 8. To find an amount from a rate, we just need to integrate that rate function. So we'll integrate from 0 to 8 the g of t function. And be careful not to add any initial conditions here or worry about the rate it's being processed. It just wants to know how much arrives during that time period. Not how much was already there, not how much is processed, just how much arrives. So that's just the integral from 0 to 8 of g of t dt. They give you 1 point already just for writing that. And then they'll give you your second point here for the value, which we'll just find on our calculator. So we hit math. You're going to go down to option number 9, or just hit 9. And now we want an integral from 0 to 8 of, well, that same exact function, which was 90 plus 45 times the cosine of x squared over 18. And we put our dx out there. We integrate it, and it tells us it's 825.551. And that's tons of gravel. And there's our second point there, just for getting the right value from our calculator. For part C, it wants to know, is the amount of unprocessed gravel at the plant increasing or decreasing at t equals 5 hours? So I think it'd be useful for us here to have a function that represents the amount of unprocessed gravel. So the amount of unprocessed gravel should be equal to the amount of unprocessed gravel we had to begin with. So in fact, we need to name this function. So I'm just going to call it we'll just call it the capital A function. A of t, this is going to be our amount of unprocessed gravel. A of t is going to be equal to the amount we started with, 500, plus the integral from 0 to whatever t value we happen to be at of g, minus the rate at which it's being processed, which is 100, right? 100 tons per hour. So that's what the amount of unprocessed gravel is equal to. And we'll find this is actually going to be useful for us in part D when they ask for the maximum of this. But for right now, to determine if a function is increasing or decreasing, we need its derivative, right? A prime of t. So a prime of t, well, 500's derivative is 0. And the derivative of an integral from a constant to a variable of some function is just the function. That's the first part of the fundamental theorem of calculus. So the function is just g of t minus 100. So the derivative of the amount function is just g of t minus 100. So we want to know, is g of t minus 100, is it greater than 0 or is it less than 0? Because that will tell us if this function a is increasing or decreasing. And we're looking for that at t equals 5. So at t equals 5, right, we have g of 5 minus 100. And so we'll just take a look at g of 5 minus 100 in our calculator. So we had 90 plus 45 times the cosine of, if we're evaluating this at 5, that's going to be 25 over 18. And then we're subtracting 100 from that. And we end up with negative 1.859. And so since that's negative, we can say, so the amount of unprocessed gravel is decreasing at t equals 5. And we'll give a reason, because we can either say a prime of 5, which is g of 5 minus 100, is less than 0. And they're going to give you 2 points for this. One, just for any sort of comparison of g of 5 to 100. Right, so this over here, and 1 with the answer that it's decreasing because that value, g of 5 minus 100, was negative. And now in part D, we want to find the maximum amount of unprocessed gravel during those hours of operation. So we had the function already. A of t was equal to 500 plus the integral from 0 to t of g of x minus 100 dx. So to determine when a function is at its maximum, you need to take a look at its derivative. right? And we already knew that a prime of t, we already did this, was also equal to g of t minus 100. So we want to know, when does that equal 0, right? Critical values of a function tell you when it might be at a max or a min. So now we just need to graph g of t minus 100 and see when it's equal to 0. So we'll go into the y equals screen here, and g of t is our original function, right? 90 plus 45 cosine of x squared over 18. And then we wanted to subtract 100 from that. And we want to do this on the window from 0 to 8, right? Because we don't care about anything outside the workday. So I'm going to hit window. And actually, from a previous problem, I already have it set to an x min of 0 and x max of 8. Normally, this says negative 10 and this says 10. And so you want to go in and turn that into a 0 and an 8. And then we'll hit graph. And we can see that there's only one intercept there, just a little bit before 5, it looks like. And so we want to find that value. And so we'll do second trace, and we'll pick option 2, which is 0. And it'll say left bound, and we can see it's at x equals 4, which we need to go a little bit closer to the right so we can see our cursor. There it is. Just go till you're to the left of it, and you can see the cursor. Hit enter. And then scroll to the right until you're to the right of that intercept. Okay. And you can hit enter. And then it says guess, so hit enter one more time. And you get 4.9234803. So we can go back here and say that this is true when t is equal to 4.9234803. And they want you to justify your answer about what the maximum amount is. And you have two options here. And we know when the maximum could occur. It can occur at this critical value of 4.9, or it could occur at the endpoints of 0 and 8. So we have two options to find out if it's a maximum there or at the endpoints. We can just make a chart of values, right? We can just evaluate a of 0, a of 4.9234803, and a of 8, and see which one is the largest. So we'll do that first, right? We know what a of 0 was. At the beginning of the day, there was 500, so we don't really need to do anything for that. To find 4.9234803, to find that value, we'll just go to our calculator. We'll go out of our graph, and we're just going to do our function a, which was 500, plus the integral, so math, option number 9, and the integral from 0 to that value that we found, which was 4.9234803 of our function. Instead of having to rewrite that g minus 100, the nice thing is we've graphed it. It's in the y1 screen here. So what I can do is, once I get back to my parentheses here, I can hit this VARS button next to the clear and go to the second column and choose option 1, function. And then we can see we have the list of our functions. We'll just put y sub 1 in there. That was our function. That's what we want to integrate. And then dx. And when we do that, we get 635.376. And then we can do the same thing again at 8. But what I'm going to do is I'm not going to bother to retype it all. I'm just going to go up and highlight that and hit enter. It brings it all the way back down. It has everything I want exactly the same, except what I want was I want to have an 8 up there in my upper limit rather than that 4.9 number. So we just change that to an 8, hit enter, and we get 525.551. And so since our only possibilities were the critical value and the endpoints, we can see that the maximum amount is 635.376. Now, that gets us all 3 points for this. 1 for considering when a prime was equal to 0, 1 for finding the correct answer, and 1 for the justification which is this little chart here of values of all the possibilities. Now, you could have also only looked for the value at the critical value, because if we look at our graph, we knew that the derivative, we graphed the derivative here, right? G minus 100. We knew that the derivative was positive for that whole first portion, and then it was negative for everything after that. And so if the derivative is positive, then the function is increasing, and if the derivative is negative, the function is decreasing. So we could have said something like a prime greater than 0 on 0 to 4.923, and a prime less than 0 on 4.923 to 8. So a increasing, then decreasing. You'd write this out a little bit nicer. So a is increasing on that interval and then decreasing on the second interval. Thus, the max must be at 4.923. And then you would just go ahead and only check the value at 4.923, which you'd get 635.376. And then your justification would be this instead of the chart with all three values. But either way you choose to do it is fine, and you'll get all the points, whichever one you choose, as long as you do it correctly. So that is it for this rate FRQ, question number 1 from the 2013 AP Calculus AB exam. All right, this is question number 1 from the 2015 AP Calculus AB exam. It's a rate FRQ, where they give us this function R of t that models the rate at which rainwater flows into a drain pipe in cubic feet per hour, or t is in hours. And we're looking at from 0 to 8 here. It says the pipe is partially blocked, so the water drains out the other end at this other function, and it's a rate modeled by d of t, capital D of t, also in cubic feet per hour. And it also tells us that at t equals 0, we have this initial condition that there are 30 cubic feet of water in the pipe. We want to know how many cubic feet flow into the pipe during this 8-hour interval. We don't care about how much drains. We don't care about how much is in it, right? We don't have to include our initial condition. We just want to know how much flows into it during that time interval. So in order to figure out the amount that flows in, we just have to integrate the rate at which it flows in. So we're going to do an integral from 0 to 8 of capital R of t dt, which is a nice little integral to do using, you could do it by hand, but since it's a calculator question, there's no reason not to just punch it into your calculator to make sure you don't make a little mistake on it. So we'll go to our graphing calculator, we'll hit math. We'll go down to option number 9. You can also just hit the 9. We're going to integrate from 0 to 8. And the R of t function that we had was 20 times the sine of t squared over 35. I'm going to hit alpha and the x button just to give me a nice fraction. You don't have to do that. And we're going to use x, so x squared over 35. Close your parenthesis for the sine. And put your dx out there. And it tells you that it's 76.570. And if you're not getting that value, just check and make sure you're in radians, not degrees on your calculator. You should always be in radians. So we get 76.570. And they gave you 2 points here for this, one for the integral setup and one for the value. In part B, it asks us, is the amount of water in the pipe increasing or decreasing at t equals 3? In other words, it's saying, is the rate at which it's flowing in greater than or less than the rate at which it's draining out? So we just want to know, is R of 3 minus D of 3 positive or negative, right? If it's positive, then the amount of water is going to be increasing. But if it's negative, then the amount of water is going to be decreasing. So we're just going to find R of 3 minus D of 3. They give you 1 point just for like setting that up, right, considering those values. And so now we'll just evaluate this on our calculator, right? R was 20 times the sine of t squared over 35. So if we're doing this at 3, that'll be 3 squared, or 9 over 35. And then we can get that value. And then we can just subtract from it the value of d at 3. So I'm going to put that whole function in parentheses. So it was negative 0.04 times t cubed, so 3 cubed, or 27. And then it was plus 0.4 times t squared, so 0.4 times 9, right, since it's 3 squared. And then plus 0.96 just times t, so times 3. We'll close our parenthesis there for the end of the d of t function. And we end up getting this value of negative 0.31. We'll round to negative 0.314. We'll say approximately equal to negative 0.314. We'll say that's less than 0. So, since r of 3 minus d of 3 is less than 0, the amount of water in the pipe is decreasing. And we can give ourselves 2 points there for this. One for, like we said, considering r of 3 minus d of 3, and one for the explanation here and the actual answer that it's decreasing. In part C, it wants us to find out when is the amount of water in the pipe at a minimum. Well, then we have to write a function that represents the amount of water in the pipe at any given time. I'll call that W. So W of t is the amount of water in the pipe at any t value between 0 and 8. So it should equal the initial amount that was in the tank, which is 30, plus an integral from 0 to t of the r function, right? The function that represents the rate at which it flows in. So if we integrate that rate, we get the amount. And then we should subtract from it the integral from 0 to t of the d function, the rate at which it drains out. So this function here is going to tell us how much water is in the pipe at any given time. And if we want the minimum of this function, we need to find its critical values. So we need to find the derivative of w here. Well, the derivative of 30 is 0. The derivative of an integral from a constant, 0, to a variable t of a function is just the function in terms of t. And the same with the other one. So this w prime is just r of t minus d of t. In fact, it's really the same thing we were looking at in the last problem, right? R minus d. But what we have to do is we have to figure out when does this equal 0, which means we're going to need to graph r and d and see when they intersect, or graph r minus d and see when they equal 0, when that function equals 0. So we'll do that. We'll go into our graphing calculator by hitting y equals. We're just going to put in r minus d as y1. So r is 20 times the sine of x squared over 35. So we've got that. And then we want to subtract the function for d, which was negative 0.04x to the third, plus 0.4x squared, and then plus 0.96x. And we'll close off our parentheses there. And we're only looking at the time interval from 0 to 8. So I'm going to hit window and pick an x min of 0 and an x max of 8. So that all I'm looking at is the part from 0 to 8. And if we're not quite sure what's going on over there on the far left, if it's crossing through, we should be pretty clear to us that at t equals 0, both r and d equal 0. So that intercept is just right there at the origin at 0, 0. So we really only have one x-intercept to worry about. That it's this one right here in the middle looks like between 3 and 4. So we'll hit second and trace. Go down to option 2 for 0, which is going to find that x-intercept. it starts off saying left bound. So you want to go to the left of your intercept, hit enter. When it says right bound, go to the right of your intercept and hit enter. And then it says guess, hit enter again, and it'll tell you 3.2716584 is when that equals 0. So we'll say this equals 0 when t is equal to 3.2716584. And we also know that the minimum could occur at t equals 0 or at t equals 8, at the endpoints of our interval. And so we also know, so we have two options here. There's always two options. One is to just make a chart with all your values, with your endpoints and your critical values. But the other option is to write a little statement that eliminates some of the possibilities. Right? And so we can see from our graph that the rate of change of the water, right, our function here, right, that r minus d is negative on the first part of this interval, and then it's positive on the second part, which means that the function that we were talking about, right, w, is decreasing and then increasing. So if our function decreases and then increases, the minimum must be at that critical value. So we could test 0 and we could test 8, or we could say that w prime of t is less than 0 on 0 to 3.2716584. So w decreases. And w prime of t is greater than 0 on 3.2716584 to 8. So w is increasing. And the minimum must occur at t equals 3.2716584. And it actually asks us, it just asks us for at what time is the amount of water in the pipe at a minimum. So this is sufficient for the work. But what you could also do, if you don't like that, and we got 1 point for the explanation with the justification with the answer. So like the justification is 1 point, the answer is 1 point, and just having the r of t minus d of t equals 0 is 1 point. But your other option would have been, and I'm going to show this too, is just to find the value of w at 0 and at this t value and at 8. So if you wanted to do that, you could just say, okay, w of 0, well, we knew what w of 0 was already. It was 30, so we don't have to do any real work for that. But w of 3.2716584 and w of 8, we have to actually do a little bit of work to find those two values. Well, conveniently, we have our graphing calculator. So we could just go in to our graphing calculator and go out of here and just say, well, our function was 30 plus the integral of this function we have in the y sub 1, right? R minus d. So it's 30 plus math, option number 9 for an integral. And then we'll say from 0, and for the first one, we're going to say to 3.2716584. And to put that function in, we hit the VARS button next to clear. Go to the second column, y VARS. Choose option 1 for function, and since our function is y1, we'll just hit enter there. And we'll put our dx at the end, and we'll see that it comes out to be 27.965 when you round, so I'll just throw that here. And then we can also do the same thing at 8. Now, the nice thing is you don't have to retype everything. You can just go up here, hit enter, it gives you the exact same thing again. All you gotta do is go over here and replace all the stuff in that upper limit with an 8. Hit enter again, and it gives you 48.544. And you can see that we only had 3 candidates, the endpoints, since it was an absolute minimum on the closed interval, which are both more than this value right here. And so then you would have said, okay, well, here's my justification. I found the 3 values that were possibilities, and 3.271658 gave me the smallest number. For part D, it says the pipe can hold 50 cubic feet of water before it overflows. And for t greater than 8, water continues to flow in and out of the pipe at the given rates until it starts to overflow. We want to write, and we don't have to solve it, we just want to be able to write an equation involving one or more integrals that gives the time w when the pipe overflows. Well, we already have a function that represents the amount of water in the pipe. The amount of water in the pipe is given by 30 plus an integral from 0 to t of r of x minus d of x dx, right? And so really all we have to do is just say, well, what I want here is I want to find the time w when this actually happens, right? So what I'm actually going to go in here and do is I'm just going to say I want to integrate from 0 to w, right? I need to find that w, and we'll put our functions back in here, r of t and d of t dt, and we just want this amount here to equal 50, because that's how much water the pipe can hold. And so you get 1 point just for having the correct integral, 0 to w of r minus d, and 1 point for the whole equation with the 30 plus at the beginning and the equals 50 at the end. And that is the end of this FRQ, number 1, the rate FRQ from the 2015 AP Calculus AB exam. All right, this is question number 1 from the 2016 AP Calculus AB exam. It's what I call a rate FRQ. And so we're given a chart here of values that represent water being removed from a tank. All right, so we've got 2 functions going on. We've got r of t, which is the rate at which water is removed from a tank, and we've got w of t here, which is the rate at which water is being pumped into a tank. And we know that r is differentiable and always decreasing, right? So that the rate at which the water is being removed, we know, is always decreasing. And it also tells us that at t equals 0, there are 50,000 liters of water in the tank. So first thing it wants us to do is just approximate r prime of 2, showing the work and putting units. So r prime of 2 can be approximated most easily from the chart. Right? R prime of 2 can be approximated using just the average rate of change on 1 to 3. So that'll be r of 3 minus r of 1 over 3 minus 1. And that'd be 950 minus 1190 over 2. 950 minus 1190 divided by 2 just comes out to be negative 120 liters per hour, or liters per hour squared. Either way, you can put per hour, or hour squared, and that's fine. And of course, if you want to use your calculator, since this is a calculator question, to do the arithmetic there, that's fine. But if not, that's good too. You get 1 point for the correct estimate and 1 point for the correct units. So 2 points there in part A. In part B, it asks us to use a left Riemann sum with the 4 indicated subintervals from the table to estimate the total amount of water that's removed from the tank during the 8 hours. So we'll just, since those are not equal subintervals, right, 0 to 1, 1 to 3, 3 to 6, and 6 to 8, those aren't the same number of hours each time. So we'll just do this, this approximation by finding each trapezoid separately. So we're going to take the bases of each trapezoid, that's 1340 and 1190 here in this case. So we'll write 1340. Oh, it said a left Riemann sum. That's my fault there. It says a left Riemann sum, and I was going to do a trapezoidal sum, which would be really bad, because then we'll get this completely wrong. So a left Riemann sum is just going to be the left endpoint of each interval. So from 0 to 1, it's a length of 1 times the left endpoint is 1340. And then plus 3 minus 1 is just 2. And then the left endpoint of that interval is 1190. And then from 3 to 6 is 3 hours, and the left endpoint of that interval is 950. And then from 6 to 8 is 2 hours, and the left endpoint of that interval is 740. And so we're just going to do the arithmetic there. We can punch it all into our calculator, but you're going to end up getting 8,050 liters. And that's the total amount of water, at least the approximation for the total amount of water that's being removed on that time interval. So we actually got 2 points there for that. One just for having the setup look correct, and one for having the answer. And then the second part of the question is this an over or an underestimate of the total amount? Well, remember that r of t we knew was a decreasing function, right? So if you have a function that's decreasing and you're using left endpoints of each interval, right, you're going to have rectangles that are extending over that function. And so we'll say this is an overestimate. And our reason is because r is always decreasing. And if you can say that it's an overestimate with that reason, and that's the only valid reason you can use, that gets you the third point for part B. In part C, it says to use our answer from part B to estimate the total amount of water in the tank at the end of 8 hours. Well, we know that we started at 50,000 liters, and we know that we subtracted 8,050 liters, and we're also going to add in some number of liters, right, from this function w of t. And if we're talking about the 8 hours, and how much did we put in? Well, we just integrate that rate, so it's the integral from 0 to 8 of w of t dt. So you get 1 point just for having this integral somewhere in there, and then you'll get 1 point for actually finding this final value, and it wants us to round this to the nearest liter. So we're going to go to our graphing calculator here. We're going to do 50,000 minus 8,050 that we've subtracted out of, that's removed. Then we're going to add. We're going to hit math. We'll go down to option number 9, FNINT, and we're going to integrate from 0 to 8 that function w of t, where w of t was equal to 2,000 e to the power of negative t squared over 20. So I'm going to hit alpha and the x button next to it to just kind of give me this nice little fraction up there. I'm going to say negative, since we're not using t, we're using x, we'll say negative x squared over 20, and we'll go outside of our integral here, put our dx, and get 49,786.19532. It asks us to round to the nearest liter, so that'll be 49,786. And just getting that answer there is the second point for part C. In part D, it asks us if there is a time when the rate at which the water that is pumped into the tank is the same as the rate at which the water is removed from the tank. in other words, what it's saying is there a time when W of t is equal to R of t? Right? Or it's saying, effectively, we could like subtract one to the other side. It's also saying, is W of t minus R of t ever equal to 0? And now, we know that W is continuous, right? Because we know that 2000 e to the negative t squared over 20 is a continuous function. And we know that R is continuous because it says it's differentiable, so therefore it must be continuous. And so if both W and R are continuous, then the difference between the two of them is also a continuous function. So if I can show that W minus R is positive somewhere between 0 and 8, and negative somewhere between 0 and 8, then since they're both continuous, it must have been 0 somewhere between t equals 0 and t equals 8. And the intermediate value theorem would tell me that. So we're going to say that W, and you want to make sure you state this, W minus R is continuous because W and R are continuous. First of all, right? So if you're going to use the intermediate value theorem, or at least try to, you want to state the conditions for it. And you probably want to give a reason why, right? I mean, not for W because that's just clearly a continuous function, but R is continuous. We could say it's continuous because it is differentiable. And anytime a function is differentiable, we know that it is also continuous. So what we want to try and do then is just figure out if there is a time when W minus R is positive and a time when W minus R is negative. And we've only got a few different values to test here that we could possibly test for R. So let's just start at 0. And W of 0, if you look at that, you're going to get 2000 e to the 0, or just 2000 times 1, which is 2000. So W of 0 is 2000. And R of 0 is less than 2000. So W of 0 minus R of 0 is certainly positive. So now all we have to do is find a place where W minus R is greater than 0. And so I'm just going to test the value at the end at 8, which makes the most sense to test. Well, actually, it doesn't really make any more sense than testing anything else. So we'll just test W minus R at 8. So W of 8 minus R of 8. And we know that R of 8 is 700. So we'll use our calculator to find W of 8. So W is 2000 e to the power of negative x squared. So if x is 8, that's going to be negative 64. So I'm going to use that same thing there, negative 64 over 20. And then we want to subtract from that the value of R of 8, which we knew was 700. And we get negative 618. And so we know that is less than 0. You don't necessarily have to put the value. If you do put the value, you need to be right about it. So we know that W minus R is positive, and then W minus R is negative. So we could say, so by the intermediate value theorem, W of t equals R of t somewhere on 0 to 8. Right? Because we know that there was a place where W minus R was positive, and a place where W minus R was negative. Therefore, W minus R equaled 0, like we said here, which indicated that W equaled R. And that is the end of part D for this rate FRQ. And that's the end of the problem. So that's it for number 1 from the 2016 AP Calculus AB exam. Oh, right. This is question number 2 from the 2017 AP Calculus AB exam. It's what I call a rate FRQ, right, where they give you some function that represents some rate. We've got a grocery store opening. It has 50 pounds of bananas on a display table. Make a note of that right away. That's our initial condition, right? T equals 0. We have 50 pounds on the table. Customers remove the bananas from the table at this rate f of t, from 0 to 12. F of t is in pounds per hour. T is in hours after the store opens. After 3 hours, employees start adding bananas to the table at this rate, g of t. Right, so this one's only valid, we'll note, from 3 to 12, whereas f of t was valid from 0 to 12. Same units for g as there were for f. Question A is how many pounds of bananas are removed from the display table during the interval from 0 to 2, right, from the first 2 hours. So in order to figure out how many are removed, we need to integrate the rate, right, to find an actual amount. So all we need to do is integrate from 0 to 2 f of t dt. And just for writing the integral from 0 to 2 of f of t dt, they give you 1 point. And then, of course, you're going to use your calculator to approximate that value. So we'll just punch that into our graphing calculator here. We hit math. We're going to hit option 9. You don't have to scroll down. You can just hit the 9. I'll scroll all the way down. And then we're going to integrate from 0 to 2, the f of t function, which was 10 plus, and then it was 0.8t. So since we're using x here, we're going to do 0.8x times the sine of x cubed over 1,000. And I like to do my fractions hitting alpha and then the x button right next to it to give me like a nice fraction bar. And then we'll do x to the power of 3 divided by 100. And close the sine parentheses and go over here, hit a dx out there. And when we integrate that, looks like we get 20.051. And so we can just go right here. We can say it's about 20.051 pounds. And it doesn't ask for units, so you don't really need the units, but it's always nice to have them. We get 1 point for that answer. For part B, it says find f prime of 7. And then using correct units, explain what it means. So first we'll find the value, then we'll talk about what it means. So since we're using our calculator here for this problem, all we have to do is go into our calculator and have it find f prime of 7 for us. We're going to hit math, and we're going to go down this time to option 8 in deriv. And we're going to take a derivative with respect to x of our function, which was, again, 10 plus, and we'll type in that exact same function, 0.8x, times the sine of x to the 3rd power over 100, and close your parentheses. And I believe we were looking for it at 7. I'm going to hope that's right. If not, we'll go back and fix it. At 7, we got negative 8.120 if you round. So let's hope that's I hope it was 7. Ah, good, it was 7. So f prime of 7 is equal to negative 8.120 when we rounded it there. We get 1 point here just for getting that correct value. And it wants us to then, using correct units, explain what that means in the context of the problem. And so, well, it's the derivative of f. And f is the rate at which the bananas are being removed from the display table. So the derivative is the rate of change at which those bananas are being removed. So what we'll say is at t equals 7, or even better maybe saying something like after the store has been open 7 hours, that'd be even better maybe. After the store has been open 7 hours, the customers are removing, well, actually we'll say the not just the customers, but we'll say the rate, this will be even better, the rate, because that's what it is. We're talking about this rate, how it's changing. The rate at which customers remove bananas from the table. And since our rate is negative 8.120, we're going to say that rate, the rate is decreasing. Okay. And that's, the rate is f, and so its derivative was negative, so that rate is decreasing at negative 8.120, and make sure we put our units, which are bananas. Oh, that's not bananas, it's pounds of bananas per hour. That's the f of t units. And so when we take the derivative with respect to t, we have to add another per hour here. It's kind of like an acceleration, but don't say acceleration. It's not acceleration, right? The units are like the units of acceleration, but it's just that the rate in pounds of bananas per hour is decreasing at negative 0.8120 per hour. And so it's pounds of bananas per hour per hour. And they gave you 2 points for this, one for the value that we already found and one for the description of what it means using the right units. For part C here, we want to know, is the number of pounds of bananas on the table increasing or decreasing at t equals 5? Well, the number of pounds on the table, and we'll come up with a new function for this, the number of pounds of bananas, we'll call it B. B of t is equal to the number of pounds of bananas that were on the table to begin with, that's 50. B of t is going to be 50 plus however many pounds they've put on. So the integral from 0 to t of f minus the integral of g, right? The amount that have been, oh, actually, sorry, I've mixed that up. It's minus the amount that have been removed. So this one should be a minus. Subtracting that, and then we're adding the integral of g, right? And for g, we got to be careful because that one's from 3 to t, not from 0 to t. And we want to know, is that function increasing or decreasing at t equals 5? Well, you can determine if something's increasing or decreasing by looking at its derivative, b prime of t. The derivative of 50 is 0. And then both of these are derivatives of integrals from constants to a variable of some function. So their derivatives are just the functions. So it's negative f of t plus g of t. And so what we want to know basically is g of t minus f of t positive or negative at 5? So we'll say, let's look at g of 5 minus f of 5 and see what it equals. Well, we'll then have to go in and evaluate g of 5 minus f of 5. So we'll go to our calculator here. G of 5, g was 3 plus 2.4 times the natural log of, and it was t squared plus 2t, so 5 squared is 25. And then plus 2t, 2 times 5 is 10. I could have put 35 there, but this is good enough. So that's g of 5, that number. And then we'll subtract from that f of 5, which was 10, plus, and then it was 0.8t, or 0.8 in this case, times 5. And then times, oh, we don't need that. We'll just put our sign. Oh, that's not the sign button. Let's try that again with the actual sign button. Sine of, and then it was t cubed. So 5 cubed is 125 over 100. We don't need to bother to reduce that. The calculator will do it for us. Close our parentheses, and we end up getting negative 2.263, which is less than 0. So that tells us that B, the number of pounds, is decreasing. So the pounds of bananas on the table is decreasing at t equals 5. And we want to, we'd note that that's because this is less than 0. And that was worth 2 points again, 1 for considering f of 5 and g of 5, and 1 for the answer with the reason. And here in part D, we want to know how many pounds of bananas are on the display table at t equals 8. Well, we already wrote a function to represent pounds of bananas on the table. That was function b. b of 8 is what we're looking for. So b of 8 should be 50 minus the integral from 0 to 8 of f, and then plus the integral from 3 to 8 of g. And so all we have to do is set that up, and they actually gave you 2 points here for setting that up correctly, and then 1 point for getting the answer, our final answer. And so we'll go into our calculator here. We've got 50 minus, and it was an integral, so math option number 9, and it was the integral from 0 to 8 of f of t. And of course, once again, f of t was 10 plus, and then it was 0.8x times the sine of x cubed over 100 dx. And then we needed to add to that the integral, so math. And we'll go down again to option number, that's way too far, option number 9. And it's now an integral from 3 to 8 of our other function, which was 3 plus 2.5 times the natural log of x squared plus 2x. Close the natural log parenthesis. We've already got the closed parenthesis there for the end of the integrand. We'll put our dx there, hit enter, and hopefully we've typed it all in correctly and got 23.347 pounds. Of bananas. And that gives us 1 more point for getting the actual answer. That's all 9 points here for question number 2, this rate FRQ from the 2017 exam. All right, this is question number 1 from the 2018 AP Calculus AB exam. It's about people entering a line for an escalator at a rate modeled by this function r of t. And it's one of the ones that I call a rate FRQ. And it's a calculator question here. So r of t is measured in people per second, t in seconds. People get on the escalator and then they exit the line at a rate of 0.7 people per second. And we know that there are 20 people in line at t equals 0. So part A just asks us how many people enter the line for the escalator from t equals 0 to t equals 300. Well, in order to figure out the amount of people, you just have to integrate the rate. So all we need to do here is an integral from 0 to 300 of r of t dt. And of course, r of t here is this nice little function from 0 to 300 of 44 times t over 100 cubed minus, or times 1 minus t over 300 to the 7th. So we'll just use our calculator to figure out what that integral is. So we'll go to our graphing calculator, and we're going to do math and option 9. And again, you can just hit the 9, but I'll scroll down to it. Option 9. And we're going to integrate from 0 to 300 of that r of t function, which was 44. And then inside of some parentheses, we have, I'm going to use alpha and then the x button to give me a nice little fraction here. X over 100. We'll close that parenthesis and raise it to the 3rd power. And then we're going to multiply that by, in a new parenthesis here, 1 minus, and we're going to get another fraction with the alpha x button. And then it'll be x over 300 this time. And then when we close that one, we're going to raise that one to the power of 7. And we'll throw our dx out there at the end, of course. And that ought to give us our answer, which is 270. Actually came out to be a real nice number there. So we'll say that is equal to 270. And that was worth 2 points. 1 point for the integral setup and 1 point for getting 270. Part B asks us, how many people are in the line at t equals 300? And it says during that time interval from 0 to 300, there are always people in line. So if we want to know how many people are in the line, well, we have to add together three things. One is the number that started in the line, and then plus the number that entered the line minus the number that left the line. Well, the number that started in the line was 20. The number that entered the line, we just found that value, right? The value, that was the integral from 0 to 300 of r of t, right? So that's 270 entered the line. And then we need to subtract the number that left the line. And the number that left the line is just going to be 0.7 per second. That's a constant rate. So you can either write it out as an integral of 0.7 dt from 0 to 300. But if we think about that, that's just 0.7 times 300. Right? So really this is 290 minus 0.7 times 300. And 0.7 times 300 is 210. So we've got 290 minus 210, which is 80. We should have had 80 people are in the line at t equals 300. And that part was worth 2 points. One for considering the rate at which they left, right? So having this minus this integral, or just the 0.7 times 300. And then one for the final answer of 80. For part C, it asks us, when is the first time that there is no one in line for the escalator? And so we can see that r of t after 300 is just equal to 0. So no one else is entering the line after t equals 300. And since we had 80 people in the line at t equals 300, we can find out how long after t equals 300 there was no one in the line, which would just be 80 divided by 0.7. Right, we're just going to divide the number of people in the line by how long it takes people to exit the line, 0.7 people per second. And then, of course, that tells us how long after t equals 300. So we'll want to add 300 to that, right? So this is the time after 300. And because we had 80 people, leaving it 0.7 people per second. And then we'll add the 300 to that. And we'll need to use our calculator there, I guess, to do, we don't have to, but it'll be easier to do 80 divided by 0.7 on our calculator. And since we have it, you might as well use it, 80 divided by 0.7. And then we'll just add 300 to that, which is, of course, 414.286 seconds. And part C there was just worth 1 point for getting the correct answer in the end. And part D wants us on 0 to 300 to figure out at what time t is the number of people in line a minimum, and to find to the nearest whole number the number of people in line at that time with a justification. So what we need here is a function to represent the number of people in the line at any given time. And so the number of people in the line at any given time is just going to be the number that started in the line plus the number that entered the line, right, which is going to be an integral from 0 to whatever t value we're talking about of r of x dx, and then minus the we could say the integral from 0 to t of 0.7, or we could just say, since the integral from 0 to t of 0.7 dt is just 0.7t. We could just say minus 0.7t. And so this is our function. We'll call it capital L of t. It's the number of people in the line at any given time. And we want to know when is that function, capital L, at a minimum. So we have to take L prime. Well, L prime is just going to be r of t. That's the derivative of the integral from 0 to t of r of x dx. Right? The derivative of an integral from a constant to a variable t of a function is just the function in terms of t. And then, of course, minus the derivative of 0.7t, which is just minus 0.7. So we can be at a minimum, or we would be at a maximum here, when r of t minus 0.7 is equal to 0. And so we're going to need to figure out when that's true. So what we'll do is we'll graph r of t minus 0.7 and look for its x-intercept. So we'll do that on our graphing calculator here. So we'll hit y equals, and of course our function was 44, and then it was the parenthesis here with our alpha and our fraction bar, x over 100 to the power of 3, and then parenthesis, we've got 1 minus, and then we've got x over 300 here, and we'll raise that to the power of 7. And don't forget that we had a minus 0.7 there that we needed to have at the end. And we're going to graph this. We want to look at this from t equals 0 to t equals 300. So we're going to change our window here. We're going to hit the window button and put our x min of 0 and our x max of 300. Now when we hit graph, we get this nice little graph here. With a couple of different t values. We're going to mark both the t values. So we're going to say second trace, and option 2 is 0 to find the 0 or the x-intercept. And I'm going to scroll. Well, I'm just going to start here since I'm already to the left of the second one. I'm going to hit enter, and I'm going to go over to the right of that intercept and hit enter, and then I'll hit enter once more, and we get 166.57. 472. So one of our values is going to be 166.57472. And then the other one is going to be t is equal to, and we'll go back in here, we'll do second trace again, option 2 for 0. And this time we're going to have to scroll all the way back here until we get to the left of that other x-intercept, which we have now done. We'll hit enter. We'll go to the right of that x-intercept. We'll hit enter, and we'll hit enter again, and we get 33.013298. So we got t equals 33.013298. So we got two options there. And so far we've gotten 2 points here. 1 point for setting r of t minus 0.7 equal to 0, and 1 for identifying this value here. And so if we think about this, we're looking at a graph of the derivative here. And the graph of our derivative tells us when the function is increasing or decreasing. And our function is the number of people in the line. So the derivative is negative from 0 to 33, which means that the number of people in line is decreasing. Then the derivative is positive until that next x-intercept, which means the number of people in line is increasing. So we know that based on our sign chart, right, L is going to decrease, then it's going to increase, then it's going to decrease. Right? That's what L is going to do here. And so the only possible places when we could have a minimum would be at t equals 33.013298, or at t equals, what was it there, 300. And we already know that at t equals 300, we had 80 people in the line. We already figured that out. So what we're going to do here is there's two options. One option is just to evaluate our function here at all of our four values at t equals 0, t equals 166, t equals 33, and t equals 300. Come up with a chart with four values and pick the one that's the smallest. The other option is we can eliminate 166.57472 because we know that one is a maximum. And so I think that's going to be easier. And also we can eliminate the value at t equals 0 because we know that's a maximum as well. So what I'm going to do is I'm going to say that L prime is less than 0 on 0 to 33.013298. So L is decreasing. L prime greater than 0 on 33.013298 to 166.574719. So L is increasing, and you should write out decreasing and increasing all the way. And then we know that L prime is less than 0 again on 166, got ahead of myself there, 166.574719 to 300. So L is decreasing again. The minimum can only occur at t equals 33.013298 or at t equals 4. Now we already know that L of 4, we already found that, the number of people in line. Sorry, I don't know why I wrote t equals 4. Why am I thinking 4 here? T equals 300. And we already know that L of 300 is equal to 80. We found that earlier here. And so now we just need to find L of 33.013298, which should be, well, our L function was 20 plus the integral from 0 to 33.013298 of r of t dt, and then minus 0.7 t. And what I'm going to do here is I'm going to put that 0.7 inside of this integral this time. So minus 0.7, all of that inside the integral dt, because what I have graphed in my graphing calculator, we'll note, right, is r minus 0.7. So now when I go out of here, I'm going to do 20, and we'll do plus the math, option 9, add the integral here, from 0 to 33.013298 of, now instead of having to retype it all, since I have r minus 0.7 in as y1 in my y equals screen, I'm going to hit VARS on my graphing calculator, go to the second column. I'm going to pick function and y1, and it just throws it right in there. We'll integrate it with respect to x, and we should get 3.803, which is smaller than 80. Right? So we'll say equals 3.803. And we'll note that that is less than 80. Right? So L of 33.013298 is less than L of 300. And so we still need to state that we'll say something like the number of people in line is at a minimum at t equals 33.013298 seconds when there are 4 people in line because it said to round to the nearest whole person. And you want to write out a little statement like this. It doesn't have to be fancy. Just make sure it answers the question. Your last 2 points were for the answers here of 33.013298 and 4 people in line. And the other point is for the justification, which is all this work we did and all this writing, basically this whole page over here. And again, if you don't want to write out all of this, right, and that the minimum could only occur at these values, then you can just test all 4 values that we have, right? T equals 0, the 2 intercepts 33 and 166.5, and also test at 300. But eliminating 2 options with an explanation works as well, and then you don't have to type so many things into your calculator. And that is the end of this rate FRQ. All right, this is question number 1 from the 2019 AP Calculus AB exam. It's what I call a rate FRQ, where they give you a function that represents a rate of something. So we've got fish entering a lake at a rate modeled by this function E of t, 20 plus 15 sine pi t over 6. And we also have fish leaving the lake at a rate modeled by L of t, which is 4 plus 2 to the power of 0.1 t squared. And we've got these functions that are measured in fish per hour, and t is in hours since midnight. So question A here is asking how many fish enter the lake over the 5-hour period from midnight to 5 a.m. So from t equals 0 to t equals 5. Well, in order to figure out the number that enter the lake during some time period, we have to integrate the function that represents the rate at which they enter the lake from 0 to 5. So just writing out this, an integral from 0 to 5 of E of t dt gives you 1 point. And make sure you don't also include the amount that leave. They're asking specifically how many enter. It doesn't matter how many leave. And so then all we need to do is figure out what the value of that function is, what the value of that integral is. Okay? And so we'll just use our calculator to figure that out. And so we'll go into our graphing calculator. We'll hit math. We'll go down to option number 9. We're going to integrate from 0 to 5, and we're going to integrate that E of t function, which was 20 plus 15 times the sine of pi times t, and we're using x here, since our calculator will do this in terms of x, pi x over 6, and then doesn't really matter, but we'll close our parenthesis there on the argument of the sine. We throw our dx out at the end, and we integrate. We get 153.458. And so that's 153.458. 458 or 540? 458, good. And it says to the nearest whole number, so we're going to say 153 fish. That's how many fish enter the lake from midnight to 5 a.m. And that's with the second point right there. Make sure you do give the number rounded to the nearest whole number, since that's what it asks for. For part B, it wants to know the average number of fish that leave the lake during that same 5-hour time frame. So the average number of fish that leave the lake should just be 1 over b minus a, right? So 1 over b minus a is how we start off these average value problems. And then we've got our L of t function here that we're going to integrate from 0 to 5. Okay? And so that ought to give us the average number of fish that are leaving the lake per hour. Right? So this is it's the average of the rate. It's the average number of fish that leave the lake per hour. It's not just the average number of fish. It's the average number of fish that leave the lake per hour. So this is the average of the rate. And so we'll just go into our graphing calculator and we'll do that. We'll put a 1/5 out in the front, 1 over 5 minus 0. We'll hit math. We'll go down to option number 9 again. We're going to integrate from 0 to 5. And our function this time is the L of t function, which was 4 plus 2 to the power of 0.1 t squared. We'll use x since that's what we're using here for our problem. And we'll put our dx out at the end, and we'll get 6.059. This time it doesn't say anything about rounding, right? So we'll say 6.059. That's the average number of fish that leave the lake per hour on this interval of time. And we get 2 points here, 1 for the correct setup and 1 for the final answer. For part C, it says, at what time between t equals 0 and t equals 8 are the greatest number of fish in the lake? And so in order to figure out when we have the greatest number of fish in the lake, we need a function that represents the number of fish in the lake. So the number of fish that we have in the lake at any given time is going to be, I'll call it capital F, fish in the lake. So we'll call this f of x is equal to the integral from 0 to whatever x value. We'll call it, in fact, let's do this actually as f of t. We'll call it the fish at any given time period is equal to the integral from 0 to t of the rate at which they enter minus the integral from 0 to t of the rate at which they leave the lake, right? Because if we integrate the rate they enter, that gives us how many have entered. If we integrate the rate they leave, that gives us how many have left. And if we find the difference between that, that tells us how many fish are in the lake. So in order to figure out when this function, capital F, is at a maximum, we need to find f prime. Well, f prime of t should just be e of t minus L of t. That's the fundamental theorem of calculus, right? The derivative of an integral from a constant to t of a function is just the function. So effectively what we are looking for is times when e of t minus L of t is equal to 0. Those are the only times when we could possibly have a maximum number of fish. And we get 1 point just for having this e of t minus L of t is equal to 0. Now in order to actually find that value, what we need to do is we need to graph both e of t and L of t and see where they intersect, or we need to graph e of t minus L of t and see when it has an x-intercept on the interval that we're talking about, which is from 0 to 8. So we're going to go into our graphing calculator. We'll hit y equals. We'll just put in our e of t function, 20 plus 15 times the sine of pi x over 6. And then we can type the other function down here. In fact, let's not do that. Let's just subtract here. We'll subtract our second function. We could set them equal to each other and see when they intersect, but we'll subtract the second function. So we're subtracting the quantity 4 plus 2 to the power of 0.1 x squared. And so that's what we're looking at here is e of t minus L of t that we're graphing. And I'm going to graph it on the window when I'm hitting the window button there. X min is 0 and X max is 8 because that's really all I care about. And I can see that it just has the one time when it crosses through the x-axis. So in order to find that, we're just going to hit second and then trace. And we're going to use option 2 for 0 because that finds us the 0 or the x-intercept. And we can see right now we're set at x equals 4. So we can see that clearly our intercept is to the right of that. So I'll just go to the right, which you can't really see that I'm doing, until my cursor is on the screen and clearly to the left of my x-intercept. I'll hit enter. Now it says right bound. I'll go till I'm to the right of the x-intercept and I'll hit enter. And I'll hit enter once more and we get 6.203564. So we'll mark that value as the t value. T is equal to 6.203564. 0, 3, 6, 5, 6, 4, 4, I believe is what it was. 5, 6, 4, 4. Let's make sure that was right. Yeah, 5, 6, 4, 4. So that's our t value. And we can, from here, now that we've found this value, we've got two options. One is just to evaluate our function at 0 and this t value, and at 8 and see which one is the largest value. Or the other option is to note that the derivative of this function, right, was positive from 0 to 6.2 and negative from 6.2 to 8 because we didn't have any other intercepts. And therefore, the number of fish had to be increasing from 0 to 6.2 and decreasing from 6.2 to 8. So, like I said, one option is just to plug this, plug in 0 to both of these and get 0, and plug in 6.2 and find out how many fish were in the lake then and how many fish were in the lake at 8 and pick the biggest. But I'm going to say that f prime of t is greater than 0 on the interval from 0 to 6.2035644. So number of fish is increasing, and f prime of t is less than 0 on 6.2035644 to 8. So the number of fish is decreasing. Therefore, the max must have been at 6.2035644. So we'll say, so max number of fish is at t equals 6.2, 6.203 5644. 5644. And that is our answer. And we get a point for the answer and a point for the justification. It doesn't actually ask how many fish are in the lake. So there's our answer with a point for the justification here as well. And you'd get the same point if you evaluated your f function here at 0 and this t value, and at 8, you'd see that the largest result would be here at 6.2035644, and you'd get the same number of points for it. So either way is fine. And of course, you'd evaluate that function using your graphing calculator. So for part D here, the last little part, it says, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? So it's the rate of change of the number of fish in the lake increasing or decreasing. Well, the rate of change of the number of fish in the lake is just E of t minus L of t. So we're wondering, is that function increasing or decreasing? Well, in order to figure that out, we need to do E prime of t minus L prime of t. We need to determine if that is positive or negative. And so we'll go in here, and we've got the functions E and L, or actually we have E minus L already written in here as y1. So what we'll do is we'll just find math option number 8, the derivative with respect to x of our function, and we can get that function E minus L by hitting VARS right next to the clear button, going into y VARS, the second column, option 1, and then choosing our y1 function. That's E minus L, and we want to know its derivative at 5. Well, if we do that, we get negative 10.728. And you don't have to show the work for that, just show the work that you found E prime minus t, or E prime of t minus L prime of t at t equals 5. We could say that's negative, and so we'll say, so the rate of change of the number of fish in the lake is decreasing because that number is negative, at t equals 5. And that is worth 2 points. 1 just for considering e prime of 5 minus L prime of 5, and 1 for the answer of decreasing with the explanation. And that is the end of this question number 1 from the 2019 AP Calculus AB exam. That's a rate question, and that's the end of it.